So in today's video, we're going to go ahead and see how we can use different trigonometric identities to help evaluate these complicated looking trigonometric integrals. And so let's just go ahead and actually delve right into this. And so over here, we're taking the definite integral from 0 to pi of cosine squared of x. And so essentially here, what we're going to do is we're going to try to find an identity involving cosine squared of x that really simplifies the integration process. Because really, off the top of my head, there really isn't anything that we can take the derivative of to obtain cosine squared of x. So it definitely does require a bit of algebraic manipulation. And so over here, cosine squared of x, the first identity that comes to mind is the Pythagorean identity. But we know that if we were to use that, then we're just going to end up with something in terms of sine squared of x, and then that's its own problem. And so instead, what we can do is we can think of maybe the double angle identity. So we know that cosine of 2x is just equal to 2 cosine squared of x minus 1. And so we have that in mind, and then we can just go ahead and solve for cosine squared of x. So we'll add 1 and then divide by 2. We get cosine squared of x is equal to cosine 2x plus 1 divided by 2. And so that right over there is a sort of just a different form of this identity that we have, the double angle identity for cosine. And so now that we have this in mind, we can just go ahead and substitute. So here this is just equal to the integral from 0 to pi. I can take the 1/2 outside just to make it a little bit less complicated. And then we have cosine 2x plus 1 dx. And now this is significantly easier to evaluate than the integral we had before of just cosine squared of x. We have a lot more to work with here. And so let's go ahead and just continue now. We can just continue to integrate as we would, any normal integration problem. So this is just 1/2. Here we know that cosine 2x, we know that the derivative with respect to x of sine of 2x is equal to 2 cosine 2x, or that if we take 1/2 to both sides, then we get cosine 2x is just 1/2 the derivative of sine of 2x, and so when we integrate, we just get 1/2 sine of 2x. Or you could use u substitution if you want, it doesn't really matter, but this is kind of just like a different way to think about it without formally having to do the u substitution. And then this plus 1 over here, when we integrate that, that's just going to be plus x. And then we're evaluating that from 0 to pi. And so then we can just go ahead and substitute each endpoint. So we get 1/2 times 1/2 sine of 2 pi, right, because 2x, so it's just 2 pi, and then plus x, which is pi, minus 1/2 times 1/2 sine of 0, right, plus 0. 1/2 sine of 2 pi, that just goes off to 0. 1/2 sine of 0, that's also 0, and then plus 0, so this entire term just disappears. And so we ultimately end up with just 1/2 times pi, which is just equal to pi over 2. And so that would be our final answer. And this is really how you would use trigonometric identities to help you simplify the integration process. You just have to, really the most difficult part is just observing what identity to use and figuring that out. But here, thankfully, we just know the cosine 2x identity drastically simplifies the cosine squared x integration process. And so really, like I said, it's just finding the identity at first that's the most difficult part, but the integration is actually quite simple. And so next up, we're going to be taking the indefinite integral of tangent cubed of x dx. And so first of all, we know that there are some identities involving maybe tangent squared of x. And with that in mind, we can just break this down into two, into the product of tangent of x and tangent squared of x, right, just by exponent rules, dx. And so then we can work here with tangent squared of x, because there isn't really much involving tangent of x. Tangent squared of x, we know that's just going to be equal to secant squared of x minus 1. And this actually does come from the Pythagorean identity. And so we have this in mind. Now we can go ahead and substitute. This is going to be equal to the integral of tangent of x times secant squared of x minus 1 dx. And then that's going to be equal to the integral of, if we expand over here, if we distribute, we get tangent of x secant squared of x dx. I'm just going to separate these into the difference of two integrals. That's totally valid because it's just tangent of x secant squared of x minus, and then here would be the integral of tangent of x dx if we were to separate them. You don't necessarily have to if you don't want to. And then here we can just go ahead and tackle each integral individually. So this first integral over here is very simple to evaluate because we know that the derivative of tangent of x is secant squared of x. So if we want to make a u substitution, we can say let u equal tangent of x, and then du is equal to secant squared of x dx. and then we ultimately get this being equal to the integral of u, which is tangent of x, and then secant squared of x dx is just du. So that's equal to 1/2 u squared, which is equal to tangent squared of x, if we back substitute, divided by 2. And then over here, we have the negative integral of tangent of x. We can rewrite that as the integral of negative sine of x over cosine of x. And then here I mean, there's different approaches to evaluate this, but we can just do the simplest one. We can let u equal to cosine of x. Because we have negative sign in the numerator, we can get du is equal to negative sine of x, and then this is a very simple u substitution. So this is equal to the integral of negative sine of x dx, we said is du, and then cosine of x in the denominator, so that's just u. This is ultimately equal to the natural log of the absolute value of u, which is equal to the natural log of the absolute value of cosine of x, right? We're just back substituting. And so ultimately, our final answer is just equal to tangent squared of x over 2 plus the natural log of the absolute value of cosine of x, and then plus c, right? So we just sum the two integrals up because we brought the negative sign in, so it becomes positive. And so this right over here is actually our final answer. And really all that it involved is just figuring out the identity to use, and then just some simple integration techniques here was just using kind of the fact that we can separate the integrals into the difference of two integrals, and then using a u substitution. So it is actually a rather simple integral to evaluate. And so ultimately here, really, the point of this video is to show that we can use these different trig identities to help us drastically simplify the integration process for these trigonometric integrals, as we kind of witnessed in these two cases over here. And this is especially helpful when you're taking the integral of some trigonometric function raised to a very high power. And so you can extend this to different notions like sine to the fourth of x, for example. But really, all that matters is that you know how to actually use the different trig identities to help simplify your integration process. So I hope this helps.